motion. Today I want to talk to you specifically about how to solve projectile motion problems. They are not challenging, but they are tedious. So if you thought the motion problems were tedious, these are more tedious. But it's our last topic before we can finally be done with kinematics, and I just want to get through it, to be honest with you. This will be on your actual AP exam. They will have tons of questions about this on the AP exam. They will have these in the FRQs. They will combine these with other questions. Projectile problems show up on the exam. For your class, they generally show up on the exam in one way, but we're going to learn all three different kinds of projectiles. So when I say three different kinds of projectiles, let me be very, very blunt. It's all mathematical constraints. A projectile is any object that travels with a velocity in 2 dimensions and an acceleration in 1. So I gave you that yesterday. But when I say constraints, there are simplifications to the problems that make the math easier. So one of the constraints, I call this a type 1 problem, is if an object just rolls off the top of your desk. This is a simplification to a simple projectile problem. It's very straightforward and very easy to do. This one basically is the condition where the launch angle is 0 degrees. And I call this a type 1 problem. If you've looked at the homework I produced, I tell you type 1 and type 2 to give you some practice. And I gave you all the answers so you can just kind of blow through them. It's a bunch of exercises. Look, if you do one of each category and you can do them with no trouble, you don't have to do all of them. But if you don't get the right answers, you should do them all so that you're proficient at them. They are not the hard kinds of questions, but they're there to kind of give you a practice in how to use this process. I have a process that works for these. And I want to talk to you a little bit about the process today and show you across the course of several different types of problems how to do it. This is what a type 1 problem looks like. Now, I'm going to tell you what the 3 types are just so that I have a kind of a starting vantage point. Because I call this one a type 2 problem. In a type 2 problem, the object is launched from the ground at some angle. Now, what makes this problem a simplification is that this problem is going to land someplace over here on the same level at which it took off. So I call this a type 2 problem because it too has a simplification in that delta y is equal to 0. Anytime you can work a 0 into your problem, you create a problem that has a simplification. So these are 2 simplifications to projectile problems, in which we found something that is 0 that makes it a little bit easier to solve. Of course, there has to be the full-blown problem, which I'll call a type 3 problem. These are the most difficult to solve in that there's no simplification. You got to brute force your way through all the math to get to your answer. And when I say brute force your way through the math, these often require that you have to solve a quadratic in order to get the time it takes for the object to reach the ground. They generally are a little more complicated. If you're scared away by the math, well, then continue to be scared. There's going to be math in this class. Now, I want to do these kind of in order. I'm going to do a type 1 problem, a type 2 problem, and a type 3 problem. And I'm going to talk about some variations of each. So let's start with a type 1 question. And we'll make it super simple to get us started. Consider just rolling a marble off the top of your desk. That's kind of what we're going to deal with here when it comes to the size. Let's say that I roll a little Hot Wheel car 2 meters per second off the top of your desks. Just so you guys know, your desks are about 80 centimeters tall. So 0.8 meters tall. And I'd like you to tell me, where does the object land? So I'm asking for the range of the problem. I'll remind you, this horizontal distance is called the range. I want you to start all projectile motion problems the exact same way. When you start a projectile motion problem, the very first thing you should do is set up a chart. And I want you to organize yourself. So although I tend to be very methodical, I think, in the way I try to present these, the reason I'm being methodical is I feel like it works best for you guys if you have a place to put the information you're given. So I would set up a chart, and that chart has a vertical side and a horizontal side. The vertical side is the one that's affected by gravity. So that one's going to have motion variables that are in the y direction, but those motion variables are going to have accelerated motion in them. They'll have an initial velocity, a final velocity, and all that kind of stuff. Your horizontal direction has no acceleration. So the motion variables there are just horizontal velocity, time, and range. Now, if you just wrote the chart out, great. Maybe give yourself more information so you're not full-blown lost into your homework. The left side refers to the up and down motion of the object. And almost certainly, the acceleration here will be the acceleration due to gravity. The right side is the horizontal motion of the object, the left to right motion. What you really need to nail down is this is the key. You need to have enough information to figure out how long the object is in the air. That determines the problem. Since the left side is a standard motion problem, you need 3 pieces of given information. And since the right side is just an object with constant velocity, you'll need at least 2 pieces of information over here. Generally, you're trying to find time. And you're usually going to use it from one side and plug it in the other. This particular problem is about finding range. So we are looking for delta x. I would go ahead at the start of a problem and figure out what it is you're looking for. Look, there's not many questions. It could be how fast you have to roll the car off the top of the table to hit a target. It could be how high is the table so that the car hits the ground a certain distance away. There's only 3 different variables here. So pay attention. They can ask for any one of those kind of unknowns. Now, yesterday when we first talked about it, we talked about a generalized problem that had an angle in it and an initial velocity. And I indicated to you that we need the idea of dealing with components in order to flesh out our problem. If the object is launched at an angle, then the initial y velocity is based on the sine of that angle. And if the object is launched at an angle, then the horizontal velocity is based on the cosine of that angle. This impacts almost every single problem we have that deals with projectiles. Except in this case. In this case, rolling it off the surface means I'm introducing something that simplifies the problem. I'm saying the object is being launched at 0 degrees when I say it rolls off the tabletop. That immediately makes the sine 0. So it will have no y velocity. That's the simplification of a type 1 problem, is that the y velocity is going to be 0. So in any condition where the object is launched horizontally or rolls off a table or rolls off the edge of a cliff, that's what we're talking about. It's about setting the y velocity equal to 0. That also means cosine of 0 is 1, so this is going to be my 2 meters per second. Whatever speed I give the object, that's how fast it's traveling horizontally. Now, you won't write this in your notes, but you should. When the object reaches the ground, it's still traveling sideways at 2 meters per second. I said this yesterday, but I'm going to reiterate it. The horizontal velocity doesn't change. And I will attempt to trick you on your next test in the multiple choice, and you will make mistakes. So you might want to emphasize, on every projectile, the horizontal velocity remains constant. And I'm getting a little frustrated that I have to say something 3 times before you guys write it down. Look, understand the stuff that's important here. I'm not trying to waste my breath here. I want you guys to understand there are certain things that happen. If I repeat it day by day, it's because I know you guys tend to not think about it. The vertical velocity will not be 0. It's going to be accelerating downwards the whole time. So it's going to reach the ground with some vertical velocity. I don't know what that is. But this problem is a pretty straightforward motion problem. Your job is to try and put all the numbers where they go. I've put one where it goes, and I've shown you how to find out another one. But there's other numbers here. For example, the object falls a distance 0.8 meters. right? That's the vertical displacement. It started at the top of the table, landed on the ground, so it's lower than it started. That's a vertical displacement. And it was pulled down by the acceleration of gravity. So the acceleration of gravity is going to make an appearance on the vertical side too. But because all of these are vectors, I need to make a decision about what direction I'm going to call positive and what direction I'm going to call negative. I know you guys love making up positive, but I'm going to make down positive. And I'm going to make to the right positive. It makes the most sense to me. The object was displaced downwards, and it's being pulled downwards. Seems not unreasonable to make downwards positive. At the same time, it's moving sideways. I'm going to make to the right, the positive horizontal direction. Now, in doing a projectile problem, you need enough information to solve for the time. That's what unifies these two sides together. I'll say it again. You need to find the time. That's the one thing that can be used on both sides. You have enough information to find the time now. Do so, please. I'll give you a moment, and I'll call on one of you. There yet? This is not tough. Oh, that brings me sorrow. All you people. Should have jumped to this one. That would have been where to go. Because this is 0. Which would have been 0.8 equals 1/2 times 10 t squared. So your time ends up being about 0.4 seconds. You put the 0.4 here and the 0.4 here. Now I know you guys have to go, but I'm going to finish up the question because I want you to start working on your homework. This is all there was to do. This is pretty straightforward. This is a subject that is on the exam. They use projectile motion frequently, but they use it in conjunction with other things. We need to be proficient at projectile problems. So this is how they're going to work in the kinematics. They'll do it in projectiles. There hasn't been a test yet that hasn't had a projectile motion problem on it. So you should expect to be able to do these and expect to see them on the exam. I want to start by telling you that we gave a basic outline of projectile motion yesterday, for those of you who are here for it. Today, we're going to be very specific, okay? So I want to start, I said yesterday that a projectile is an object that is launched in 2 dimensions, but experiences an acceleration in only 1. And I gave the basic projectile picture, an object being launched off of a cliff or something and landing somewhere on the ground. That basic picture looks something like this. And in this problem, there's simple things to consider. The object travels into the air, hits the ground over there someplace. Generally, we call this horizontal displacement the range. That's where it hits the ground. But there are other things here too. This is delta y, the vertical displacement. Measurement of how far below or above the object lands from where it starts. I've drawn this being launched from a high place and landing on a place below where it starts, but you could probably imagine that you could start somewhere below and throw something to someplace high, right? So I'm just picking one, but I could pick the reverse. The object's going to have an initial velocity, which I will call v0, and an initial launch angle, which I will call theta. And based on our conversations dealing with components, you should realize that this launch angle can be broken up into both a horizontal component and a vertical component. And in practice, this will always be broken up the same way. If the angle is here, then I will have a horizontal component that's lined up with the horizontal ground, and I will have a vertical component that's going to be acted on by gravity. I'll call this Vy initial, and I'll call this Vx. The vertical one gets the I for initial because it's acted on by gravity and its value will change. The x component, I just leave x because there's no horizontal acceleration in most cases, and it won't change. Something I said yesterday, that no matter where the object is along its route, the horizontal velocity stays the same the whole time. It's the vertical velocity that changes, because that's the one acted on by gravity. That's why at the launch, I call that Vx and Vy initial, but the Vy is always changing. And the last thing I brought up is that you shouldn't be surprised that when Vy is 0, you're at the maximum height. Something we talked about in the last set of problems. There are still reasons why you might want to know how high your projectile goes. There's a little trig here involved, but it's always the same trig. The horizontal component is always going to be based on cosine, and the vertical component is always going to be based on sine, assuming they give you the angle relative to the horizontal, and they usually do. That's the basics of a projectile, but I call this a type 3 problem. And the reason I do is that a lot of times they simplify the question for you to help focus you, and so will I. So I have two subsets of this problem. The first one I call a type 1 problem. And type 1 and type 2 and type 3, this is not in the book. I made this up for us to communicate. A type 1 problem is like what happens when you just like roll something off of your desk. I call this a type 1 problem. It's a simplification. In a type 1 problem, there's no launch angle. The launch angle is 0. That has pretty important implications. It means that whatever this velocity is, this starting velocity, it is your horizontal velocity. And the other implication is that your initial y velocity must be 0. Anytime you can work a 0 into your problem, generally makes the problem easier to do. So type 1 problems don't have a launch angle. But they have to have a launch height then, or they're not a projectile. So you roll something off your tabletop, you run off the edge of a cliff, your car runs off the top of a parking structure, something like that. Type 2 problems, again, a little more complicated, but not much. In a type 2 problem, I do have a launch angle. I call these type 2 though, because they have a simplification as well. These problems are launched from the ground and generally land on the ground. What makes this a type 2 is delta y equals 0. Still has a launch angle, still has a launch velocity. I still have to do a little trig, but I get to work a 0 into my problem. And that's easier. You might not fully understand why that's easier yet, but if you've been thoughtful about what we did in kinematics, then you realize that sometimes you have to use a quadratic to figure out time. These simplifications, you don't, which is what makes them easier to do. To appreciate that, let's do a sample question. I'm going to do a type 1 problem as a sample question. And I'll be doing several different practices over the next 2 days. This is just my first one. I'm going to roll a marble off the top of your desk. And we're going to roll the marble at 3 meters per second. Your desk is less than a meter tall, so we'll say it's 0.8 meters high. I would like to find out where the marble strikes the ground. There's only 3 versions of this problem. I put a bucket on the ground, how fast do I have to roll the marble to hit the bucket? There's, I roll the bucket this fast, where does it hit the ground? And there's, how high is the table if the marble hits the ground here? Those are the 3 types of problems. They ask for one of those 3 things. In this case, I'm asking you for the range. Now, what I've tried to do, and I will continue to try and do every year, is to give those of you who have difficulty being thoughtful at the onset a place to start. I never want to hear a kid tell me I didn't know where to begin. So I don't accept that. I give you a place to begin with every problem. This is no different. Because this is a projectile problem, I would encourage you to find a way to get organized. And I'm going to provide you with some organization. I like making a chart. And I like labeling the chart vertical and horizontal. Projectiles are defined by the fact that there's an acceleration in only one dimension, but the object moves in 2. So I have separated the 2 dimensions out so I can study them separately. The vertical side will have variables associated with acceleration, because that's where our acceleration is, up and down. The horizontal side will not. The horizontal side will have variables associated with constant velocity. However, the object's moving through space in 2 dimensions. So the time it takes to go up and down has to be equal to the time it takes to go sideways. In all of these problems, you're always linking together the time, which means you're often going to be asked to find the time that it takes to do something and use it in one place or the other. Now, I haven't given you anything about time in this problem, but I recognize that I'm asking of you where the object lands. The only way I'm going to be able to figure that out is if I know how fast the object's traveling and how long it travels at that speed. Now, I've given you one of those. I've told you that it travels horizontally 3 meters per second. That's a given in the problem. But I also tell you that it falls 0.8 meters to reach the ground. And that because it's on level surface, I'm telling you that its initial y velocity is 0. That's what makes it a type 1 problem. Now, you guys should probably be able to see from here that you're going to need either 3 pieces on this side to figure out the time, or 2 pieces on this side to figure out the answer. And although I only have 2 pieces of information on the vertical side, what's pulling the marble down? So it's very likely I have a 3rd piece of information. Now in my problem, I'm going to direct downwards to be positive and to the right to be positive. I know you tend to like upwards to be positive, but why? The marble falls downwards and gravity's pulling it downwards. It makes reasonable sense to me to just make downwards positive. To figure out time, I'm going to need a relationship that brings all the things on the left together. Again, if you haven't figured this out yet or haven't bothered to write it down, every projectile problem will almost always involve finding the time on one side and using it on the other. I've said that 6 times today. So when you try these at home and you say, I don't know what to do, I'm not going to believe you. I'm going to use delta y equals 1/2 at squared plus vyi times t. I don't think I have to explain that the motion equations aren't any different if they're in the y direction versus the x direction. Do I have to explain that? So we can see that this is still the same equation we've used dozens of times already. The only thing is I just need to figure out the time. And you can see why having a 0 makes this easier. Let's see. 10 divided by 2 is 5. 0.8 divided by 5, I don't know what that is. 0.16 equals t squared. Take the root of both sides. T equals plus or minus 0.4 seconds. Pretty sure. Yeah. So I'm going to throw away the negative one and realize that the time must be 0.4 seconds. You'll note that I can write it in both places, but I need it here. So delta x equals 3 times 0.4. 1.2 meters away from the edge of the table is where it hits the ground. Right? 3 times 0.4, 1.2. These are projectile problems. They're all exactly like this. This is enough information for you guys to get a jump on the first half of your homework. Try 1 or 2 before tomorrow. Come in with a little bit of practice. Please.